Today we are going to do a very important topic, inclusion compounds. We will do the definition, explanation, classification and application. So let's start. So before we come to the definition, I would like you to look at this diagram. Here we have two types of molecule. One is this. This is called a host molecule. It has a particular crystalline framework and there are cavities present, right? And into this cavity there are present guest molecule, or we can say another type of molecule, right? And whenever these host molecule and guest molecule are interacting through some kind of an interactions, such kind of a system or such kind of a compound are called inclusion compounds, right? So compounds formed by inclusion of one type of molecule called the guest molecule into the cavities of a crystalline framework of another kind of molecule called the host molecules without forming any specific chemical bond. Any specific chemical bond means like covalent bond. So here there are no covalent bond forming between the host molecule and a guest molecule. Rather, the kind of interactions I am talking about is hydrogen bonding, weak van der Waals forces of attraction. It can be ion pairing, it can be charge transfer, and so on. So such kind of interactions you can see between the host molecule and a guest molecule, and such kind of compounds or molecules are called inclusion compounds. There are some other terminologies also sometimes we use for inclusion compounds, like they are called occlusion compounds, sometimes they are called adducts, host-guest complexes, addition compounds, supramolecular assemblies. So these are all different terminology we use for inclusion compounds, right? Now, after the definition, we classify inclusion compounds in various ways. So the very first way to classify inclusion compound is on the basis of the structural feature of the host lattice, right, or the host molecule. So on the basis of that, the inclusion compounds are classified into three categories. The very first is the cryptoclathrates, right? So compounds having a cage structure, they have a cage structure where the guest molecule are included in the closed cavity, and a very beautiful example is of a cyclodextrins, and recently furans have also been included. So in your chemistry, in your advanced organic chemistry part, you might have read about inclusion compounds, and simultaneously you might have read about cyclodextrins also. So they are very important. Sometimes they are asked separately. So in the same video I have given a very small detail of cyclodextrin later on in this video, so that will be helpful for you if you would like to follow it. Otherwise, let us do the classification first. So the cryptoclathrates, for example the cyclodextrin. So here this is the diagram of cyclodextrin. This is a single molecule of cyclodextrin, and you can see there is a good cavity between the in the center of the cyclodextrin. Here there can be a guest molecule fit in, right? So such kind of system comes under the category of cryptoclathrates. Now when we have tubulatoclathrates, this is the second category of inclusion compounds. Tubulatoclathrates are divided further into two. The first is the one-dimensional non-intersecting channels. Now how do they look like? They look like this. Here we have tunnels or channels, right? We have tunnels and channels, but they are not interacting or they are not intersecting with each other. And a good example is urea. Now you might be wondering how urea can act as a host molecule, or how urea can have a cavity in the center, because urea is simple molecule. It is NH2CONH2. How it can have a cavity? So here I would like you to read this line. This is urea is a tetragonal molecule. Yes. But in the presence of a guest molecule, it crystallizes itself into hexagonal lattice containing the guest molecule in the long chain. So it looks something like this. So whenever urea, whenever a guest molecule approaches, urea has the tendency to convert itself into hexagonal lattice. So many number of urea molecules, they try to bind with each other and form this spiral type of bonding, and there are only 2 urea shown here for the clarity purpose. And because of this spiral kind of interaction, there is a cavity in the center, and in this cavity there a guest molecule can easily fit in. Here the guest molecule is an alkane, right? Here the guest molecule is an alkane. So such kind of interaction occurs when urea acts as a hexagonal, when it crystallizes into a hexagonal lattice. So remember, in the first category of tubulato clathrate, the example is urea. Now, before we move further, I would like you to tell something very interesting here. There are 2 terms. One is hard host, another is soft host. Now the difference between the hard host and soft host is very easy. From here you can very well make it out. Like cyclodextrins are called hard host because before and after the formation of an interaction or formation of a bond between the host cell and the guest molecule, there has been no difference or no change in the structural feature of the host molecule, right? The host molecule has not been changed after the guest molecule or the guest molecule appears or gets into the cavity, right? It remains the same. However, the soft host is the one which has a different structural feature or a different structure after the formation of a bond with the guest molecule. As you can see in urea is a tetragonal molecule. It's completely different before the bond formation with the guest molecule, but after it crystallizes or after it has a bond, after the guest molecule appears and it interacts with the guest molecule, it has a completely different structure feature. It crystallizes itself into a hexagonal lattice. So it is something else before and it's something else after. So such kind of host which has a different structure feature before and after the bond formation with the guest molecule, such kind of host are called soft host. And when there is no change in the host before and after the bond formation with the guest molecule, they are called hard host, right? Okay. So the second category, which is called the tubulato clathrates, the first part was one-dimensional non-intersecting channel, as I told you. We have second part, intersecting channels. So when the channels or the tubes are interacting or they intersecting with each other, they are called it comes under the category of second category, intersecting channel. And a very good example is zeolite. You all might be well aware with what are zeolites, right? I'm not going into the detail because zeolite is not our topic of today, but you all might be well aware of how zeolite, how much important they have. They have plethora of applications. They have a lot of applications, and they have so many channels and tubes and cavities present inside, and they have a very three-dimensional structure. So this is how it looks like. And the third category is intercalato-clathrates, and the such kind of compounds are layered inclusion compounds. They are layered inclusion compounds in which the guest molecules are sandwiched between sheets of the host matrix. Example is clay. You might not be very well aware of how clay looks like, the chemical feature or the structural feature of clay, but I would like you to show this diagram here. These are the sheets of the host matrix, the host molecule, and between these sheets are present nothing but the guest molecule. They are somewhat like they are sandwiched between these host matrix of the host molecule. So such kind of case are included in intercalato-clathrates. So these are three categories under which different examples have been defined or given. Now we have another way of classifying the inclusion compounds on the basis of organization of the inclusion compounds. It might feel a little bore for you that once we have done the classification, what is the need of doing it again? There is no problem, just a 1 or 2 minute of explanation of this part, and it will be very much clear to you in just 1 minute. So here you have to see that only these three words: polymolecular, monomolecular and macromolecular, nothing else. You don't have to go into this detail, only these three words will make it clear for you. Now polymolecular, monomolecular, macromolecular, it's all about the host molecule. It's basically about the host molecule. So when I was talking about urea, I told you that it forms a spiral type of or hexagonal structure when there is a guest molecule appearing or approaching, right? So it's not just the one urea molecule that has the property of turning itself into a hexagonal structure. No, there are so many urea molecules, they interact with each other to form this spiral or the hexagonal type of a framework, so that there are cavities formed in between, right? So when there are more than one host molecule needed to make such kind of a structure, then this is called polymolecular, right? So polymolecular inclusion compounds, where they are the host framework constructed using covalent bonds. Remember, it's the host framework constructed using covalent bonds. It's not the interaction between the host and the guest, that the covalent bond I am talking about. No, there is never a covalent bond formed between the host and the guest molecule, right? Specific dimension formed only in the presence of the guest molecule, right? So whenever the guest molecule is there, a particular structural feature will appear, right? So for example, if it's channel-like, it's urea; when it's cage-like, it's beta-hydroquinone clathrates, right? Now when it's monomolecular, I just told you, I have shown you the structure of cyclodextrins. Cyclodextrin is a single molecule, and in this single molecule you will see that there is a cavity present. So there is no need of so many molecules of cyclodextrin, only one cyclodextrin is enough. So one cyclodextrin and one guest molecule, it will be like host is to guest molecule, just 1:1 interaction. One molecule of host and one molecule of guest is enough to make interaction. So in this category comes the cyclodextrin, the antibiotics, certain proteins and so on. And when it comes to macromolecule, what else can come in your mind than zeolites? Zeolites are very good example. You can read it. They have a framework of a silicon oxygen or an aluminium oxygen tetrahedron forming a 3D array with many cavities and interconnecting channels. So zeolite come under the category of macromolecular. I think this is pretty easy for you people now. Now when it comes to application, the very first thing that comes in your mind regarding the inclusion compounds is the cavity. The size of the cavity. If you change the size of the cavity, we can change the way the guest molecule will interact, right? Not every kind of a guest molecule can interact with every kind of a host molecule, because the difference in size of the cavity will matter, right? So it becomes the base of molecular separation process and a chemical analysis. So here the chemically different species, constitutional isomers, positional isomers, regioisomers, stereoisomers, and even isotopic isomer, such kind of molecules can be separated on the basis of this particular principle. And this is very obvious that this can give a size selectivity. Compounds having closed melting points can be separated using the inclusion crystallization. Also, clathrates were successfully applied in the chromatography also, right? Now, inclusion compounds have been recognized as a source and reservoir of unstable species. There are many times what happened, we wanted to know the mechanism of a particular reaction, and sometimes there are intermediate or free radical involved, and we want something that can trap the intermediate or free radical. So what could be a good example then? Inclusion compounds. Inclusion compounds or a host molecule can have that property to trap the intermediate or free radical, and we can have an idea of what mechanism the reaction is following, right? And fourth point says that inclusion compound causes altered physical property of any guest molecule, which is pretty obvious, because a guest molecule is something else before. When it interacts with the host molecule, it's going to have a altered physical properties, right? And on the basis of these properties, clathrate find application in MRI, they find application in the resolution of racemic mixture. I don't have to say anything about zeolite. It has number of just I have listed few applications, otherwise it has number of. It remove atmospheric pollutants, it has ozone depleting CFCs property or harmful organics from water, and so many. They also find application as materials for superconductivity. So these were some of the applications, just some of the applications I have discussed here. Now, I just told you that I'm going to discuss in a very small time what cyclodextrins are. Cyclodextrins are structurally related natural products. They are natural products, right? And belongs to a family of cyclic oligosaccharide. You might be aware of oligosaccharides. We have monosaccharide, oligosaccharide, polysaccharides, right? So when it's cyclodextrin is a cyclic oligosaccharide with a hydrophilic outer surface and a lipophilic central cavity. So hydrophilic outer surface means water attracting outer surface. So because of the water attracting outer surface, cyclodextrin are quite water soluble, right? And that is where their applications are so very important, I'll tell you. And a lipophilic central cavity, lipophilic means lipid attracting, means not water attracting, right? Lipid attracting, just the opposite. So their cavity or the center part is lipid attracting. They have large number of hydrogen donors and acceptors. These donors and acceptors are reason for the bonding by cyclodextrins. They are formed during bacterial digestion of cellulose and consist of alpha-1 for linked alpha-D glucopyranose units. And the glucopyranose units have a chair conformation. Because of the chair conformation of the glucopyranose units, the cyclodextrins are shaped like a truncated cone rather than a perfect cylinder. So they are not perfect cylinder. I have shown you this particular structure. This is a flat structure of cyclodextrin. If you see this three-dimensional structure, it's not like a perfect cylinder type. No. Rather, this part is somewhat narrower, right? So that makes it a truncated cone. And if you can see, if you can read, the outer part is just told you hydrophilic in nature, and the inner part is apolar cavity, or we can say lipophilic central part, right? Central cavity. So because of the outer part, which is water attracting, cyclodextrins are soluble in water, right? Now this particular slide I have included just to show you where do we find cyclodextrins exactly. So there are types of drugs, there are a number of drugs where we find cyclodextrins, like alpha cyclodextrins are used in these particular drugs, and then beta cyclodextrin, 2-hydroxypropyl beta cyclodextrin, and so on. You don't have to cram this, just to show you the application of cyclodextrin. And we have, like for example, oral capsules, in the form of oral capsules, suppository, eye drop solutions, we have nasal spray, and these are the trade name. So just to show you, the cyclodextrin find application in many drugs and this and that. So what actually happens, why do we need cyclodextrin for drug solubility and complex formation? Actually what happens is that drugs sometimes have a poor solubility in water. So cyclodextrins, because I just told you they have hydrophilic outer part, so sometimes we use drug and cyclodextrin complex formation principle for drug solubility, because if a drug is not soluble in water, it means that drug is somewhat apolar in nature. So it can get into, or it can fit into the cavity of cyclodextrin. It can fit into the cavity of cyclodextrin, and cyclodextrin has a water attracting outer part, so it can easily get solubilized in water, and so we can target, or we can transfer the drug to the target part, we can say. So in aqueous solution, cyclodextrins are able to form inclusion complexes with many drugs. Taking up a drug molecule, no covalent bonds are broken or formed. The driving force includes release of enthalpy-rich water molecule from the cavity, electrostatic interactions, van der Waals interactions, hydrophobic, hydrogen bonding, release of conformational strain, charge transfer interaction, so on. I just told you there are so many types of different interactions that can be formed between the host molecule and a guest molecule. Here the host molecule is cyclodextrin, the guest molecule is a drug. And how do we come to know the stereochemistry, or how do we determine the interaction, kind of an interaction between the cyclodextrin and the drug? That we can do by using certain techniques, like for example the stoichiometry can be determined if there is a change in solubility, if there is a change in chemical reactivity of either the host molecule or a guest molecule, changes in the UV visible absorbance, in the fluorescence, or in the NMR chemical shift, and so on. So whenever there is a change, we know that all these changes there are different instrumentation, different techniques we can use to actually find out these changes, and so we can find out or determine the stoichiometry which has been formed between the drug and cyclodextrin complex, right? And finally I come to the applications of cyclodextrin. And so in the very first, I just told you, in the pharmaceutical industry, cyclodextrins have mainly been used as a complexing agents to increase the aqueous solubility of poorly water soluble drugs and to increase their bioavailability and stability. So because the drugs sometimes are very poorly dissolved in water, so we need some kind of a complexing agent, for example cyclodextrin, which can attach with the drugs and make it bioavailable, right? It can be used used to reduce and prevent gastrointestinal and ocular irritation, reduce or eliminate unpleasant smells or taste, prevent drug or drug addictive interaction, and so on. So I hope this video has some significance for you, and if yes, please subscribe the channel, and we will in a very short time I will try to make another video on an important topic, and we will meet in the next video. Till then, keep smiling. All the very best.